the very top of the sky, where blue thins into black. The universe doesn't just get bigger, it gets stranger, because far might be a trick our minds invented, a word that works on Earth, but breaks in the cosmos. So, if the universe has an edge, is there more space beyond it, or the end of reality itself? Every map needs an outer line, and the universe refuses to draw one. We can chase the fading galaxies, but the boundary may be written into light itself. We live inside a bubble of information, stitched together by photons that have traveled for billions of years. What we call distance is often a delayed message, arriving late from places that may no longer be reachable. Tonight, we follow those messages upward from the thinning air, past satellites and silence, into the deep archive of starlight. The journey looks like a straight line outward, yet it becomes a descent through time and physical law, because the universe does not present its limits as a fence, it presents them as horizons. Some horizons move as we wait, expanding the sphere of what can ever be observed. Others are more severe, lines that the future cannot cross, even in principle, as expansion accelerates. And then there is the oldest light we can see, a faint afterglow that turns the whole sky into evidence. It is not a wall in space, but a boundary in history, where the cosmos first became transparent. Beyond that veil, the story is still there, but it must be read in different ink. Neutrinos, gravity, and patterns frozen into structure. We will test whether space can be finite without an edge, curving back on itself with no border to touch. We will ask if the early universe briefly outran its own signals, stretching tiny quantum noise into the seeds of galaxies. And we will confront the most treacherous word in this search: outside. In a universe where space-time is part of the system, outside may describe a place or a mistake in grammar. This is not a hunt for a distant wall. It is an investigation into what nature allows us to define. Along the way, familiar intuition will fail, and measurement will take over, patient, precise, and sometimes unsettling, because the deepest edge may not be far away at all, but built into the speed at which truth can travel. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey from Earth's last breathable layers to the cosmic microwave background. We'll track each edge until it changes meaning. And when the maps finally run out, we'll see what science can still say and what it must leave open. We start at sea level, where air feels endless and ordinary, and the ocean's surface reflects a sky we rarely question. The climb begins slowly, and the horizon stays familiar for longer than expected, as if Earth is reluctant to let go. Wind dominates at first, pushing and tugging with a physical voice that microphones love. Then it thins into a softer, higher hush, because fewer molecules remain to carry pressure waves. Clouds flatten into a white skin beneath us, and weather becomes a distant idea rather than a lived experience. The blue above us lightens, then deepens, then starts to drain away, like pigment diluted drop by drop. As we rise, the air's density falls roughly exponentially, and each kilometer removes a noticeable fraction of what we started with. Oxygen does not vanish, but its partial pressure drops, which is why lungs struggle long before the sky looks different. Temperature shifts with altitude too, because sunlight, ozone chemistry, and convection trade dominance from layer to layer. The visuals stay deceptively calm, yet the physics is already changing in ways our bodies can't ignore. In the stratosphere, the sky still looks like sky, just cleaner and harsher, with fewer aerosols to scatter light into softness. The ozone layer absorbs ultraviolet radiation, warming this region from above and creating a strange thermal inversion. In the mesosphere, the air is too thin to carry sound well, so the world becomes quiet in a way that feels unnatural. The last breath of blue fades, and near silence takes over, not because nothing exists, but because the medium for sound is almost gone. Stars appear before the sky turns fully black, because darkness is not a switch, and our eyes are quick to adapt. The first lesson arrives early, delivered by the slow fade of color and noise. Space does not begin like a doorway. It begins like a gradient. We talk about an edge because edges are how humans make sense of change, and language often demands a clean answer. We draw lines on maps, we name borders, we assign thresholds, and then we build stories around them. The atmosphere invites that habit because it thins with height, but never truly stops in any sharp, final way. Molecules keep going, fewer and fewer, blending into the exosphere and then into the solar wind's constant flow. Even hundreds of kilometers up, a satellite still feels drag, a faint breaking that engineers must calculate. If we insist on a single start point for space, we are choosing a convention. The convention is useful, but it is not a wall. The most famous practical boundary is the Kármán line, set near 100 kilometers above sea level, and its origin is deeply pragmatic. It is named for Theodor von Kármán, an engineer who asked where aerodynamic flight becomes impossible in any ordinary sense. Above that height, a vehicle must move so fast to generate lift that it is essentially in orbit, where staying up is no longer about wings. The line ties space to aerodynamics and engineering, not to a sudden change in nature. It answers a practical question that pilots and policymakers can recognize. When does a plane stop being a plane? Even that answer is not unique, because the atmosphere refuses to cooperate with our paperwork. Some agencies use 80 kilometers and some use 100, and both numbers can be defended for specific purposes. The difference reflects intent, not disagreement about physics, because the density curve does not kink at a single altitude. Solar activity also puffs the upper atmosphere up and down, changing where thin becomes thinner on any given day. The atmosphere does not care which number we print on a certificate. It simply keeps thinning, layer by layer, into near vacuum. The edge of space, in this sense, is a human agreement about when air stops behaving like air. That agreement matters because it shapes how we imagine the world, and imagination sets the stage for every question that follows. When we say edge, we picture a cliff, a rim, a last step, and we instinctively search for a boundary we can point to. We imagine a place where you could stand and look over, with a clear before and after. That picture works for coastlines and canyons. It fails for most things that matter in cosmology. The universe does not offer us a railing, and it rarely offers us a single clean line. There is a deeper trap hidden inside the word edge, and it is subtle enough to feel like common sense. It suggests that beyond the edge, there is more of the same, just farther away, as if distance were the only barrier. In everyday life, distance is the main obstacle, and time is usually a footnote. In the cosmos, distance is only part of the story, because time and light decide what can be known. Expansion changes what far even means, because space itself is not a static stage. Some boundaries are not places, they are horizons. A horizon is a limit in connection, not a limit on existence, and that distinction changes the mood of the entire question. It can be the farthest we can see, because light has had only so long to travel since the universe became transparent. It can be the farthest that can affect us, because signals cannot outrun the speed of light, no matter how urgent the message. It can be a boundary created by the universe's expansion, where space grows faster than information can cross and causal contact breaks. Horizons are edges made of causality and time, real in their consequences, even if they are not physical walls. This distinction is the core mystery of our film, and it is why the ascent matters as more than spectacle. We can point to an edge of the atmosphere, even if it is fuzzy and conventional, and we can explain why it is useful. We can argue about 80 kilometers or 100 and still agree on the idea, because the argument is about labels. But can we point to an edge of the universe in the same way, with the same confidence? Is there a last coordinate, a final region, a physical boundary where space ends? Or is the only edge the one drawn by what we can observe? The question sounds simple until we try to follow it outward, because every step multiplies the scale. We leave the last thin air behind and enter the domain of satellites, where motion is a balance between inertia and gravity. We pass the orbits that make our daily lives possible, navigation, weather, communication, and we keep going into quieter lanes. We cross the moon's distance, where Earth becomes a bright disk, then the planets, then the outer dark, where the sun becomes just another star. We move through the local neighborhood of stars and into the broad disk of the Milky Way, a spiral city of hundreds of billions of suns. We step outside our galaxy in imagination, and the scale breaks again, because even galaxies are only the beginning. Galaxies are not scattered in a quiet, empty void, and the emptiness between them is not truly empty. They gather in groups, then clusters, then filaments and walls, tracing a cosmic web shaped by gravity over billions of years. Between them lie vast regions with fewer galaxies, but not nothing, because dark matter and thin gas still thread the gaps. The universe has structure on the largest scales we can map, and those maps are built from careful surveys and redshift measurements. Yet even those maps are limited by what has had time to reach us. The farther we look, the older the light becomes. Looking outward becomes looking back, and our telescopes become time machines with strict rules. At this point, the idea of an edge splits into two competing meanings, and the split is where tension lives. One meaning is a physical end, like the end of a road, where you could in principle arrive and stop. The other meaning is an observational end, like the limit of a flashlight beam, where the darkness is about reach. The first would be a property of reality itself. The second would be a property of our position in time and space, and of the universe's finite age. Our central question lives in the tension between them, and it refuses to resolve quickly. If we kept going, do we ever reach an end, or do we reach a limit in knowledge rather than a limit in space? If the universe has an edge, what lies beyond it, and how would we even define beyond? More space that we cannot access, because expansion carries it away faster than light can bridge. A boundary where physics changes, not gradually, but fundamentally, rewriting the rules our instruments rely on, or something that does not fit inside our idea of reality at all, which would force new language before new measurements. This is not a purely philosophical game, because the universe leaves evidence, and evidence has rules that do not negotiate. Light carries information, and its travel time sets a hard constraint that no technology can cheat. Expansion leaves patterns in the distribution of galaxies and in the afterglow of the Big Bang, a faint microwave glow that still fills space. Gravity shapes motion, and motion reveals mass and geometry, even when the mass is invisible. Our questions must be asked in ways that measurements can answer, even if the answers are unsettling, because science advances by what survives contact with data. So we begin with the nearest boundary, because it teaches the method and disciplines the imagination. The Kármán line is not a natural cliff, but it is a useful marker that connects physics to human definitions. It reminds us that boundaries can be chosen for practical reasons, and that practicality can masquerade as nature if we are careless. It also warns us that the most important cosmic boundaries may not be places you can reach with engines. They may be horizons you can only infer, edges written into what can never be observed. From here, the documentary follows a path outward and inward at the same time, because scale and meaning are braided together. First, we leave Earth and define what it means to travel in space, where speed is survival and small errors accumulate. Then we map the observable universe and learn why observation has a built-in edge set by light speed and cosmic history. Next, we confront horizons and the limits they impose on cause and effect, where too far becomes never. Then we test the shape of space and ask whether geometry can hide an end, the way a sphere has no edge, yet remains finite. After that, we face inflation and the possibility of a multiverse, where our universe is one region among many, separated by expansion. Then we ask what outside could mean if space itself is the thing expanding and if there is no external stage. Finally, we return to the only kind of answer that matters here, the answer we can defend with evidence. The ascent ends where blue becomes memory and black becomes a canvas, and the camera lingers on the thin curve of Earth below. The silence is not empty, and that is the final twist of the opening image. It is filled with signals, radiation, and the faint pressure of distant events, including particles that pass through us unnoticed. Above the last breath of air, the old idea of an edge begins to dissolve, replaced by gradients and probabilities. What remains is a sharper question, framed by physics instead of intuition. If the universe has a boundary, it will not announce itself like a line in the sky. It will reveal itself as a limit on what can be seen, touched, or ever reached. Next, we leave the Earth behind for real and measure what space demands from anything that tries to cross it. We left the last breath of blue and found no doorway, only a gradient into black. The atmosphere thinned into a fragile skin, and then it was simply gone. No sound, no weather, no up. Now we leave Earth itself, and distance stops feeling like geography. In space, the first ruler is light, because light sets the fastest possible delivery of information. It is not just a speed, but a limit on cause and effect. What can influence what, and when. If an edge exists, it will be written into what light can reach. Start close, where numbers still fit inside intuition, and the mind can still picture the gap. Earth to the moon is about 1.3 light seconds, so even a radio call has a pause. That pause is small, yet it is real, and it reminds us that now already has a delay. The moon hangs in the window like a stone lantern, and even that familiar face is slightly out of date. Earth to the sun is about 8 light minutes, so sunlight is already history when it warms skin. Every sunrise is a message that left the sun before we decided to watch it. The familiar sky is a museum of very recent past. Push outward at light speed, and the solar system collapses into a schedule. We leave the moon behind in seconds, and the sun's orbiting planets in hours. Mercury and Venus flick past like bright beads, and then Earth's own orbit becomes a thin ring. Mars arrives with its dusty red hint, then the asteroid belt, scattered rubble, not a solid wall, slides by as a sparse field of moving points. Jupiter's cloud bands and Saturn's pale rings become brief flashes, and then the outer giants fade into cold distance. We cross Neptune's distance in a few more hours, and the Kuiper belt becomes a brief corridor. Its icy objects are small and dark, yet they mark the solar system's lingering outskirts. The sun's domain feels large until we time it. Then the solar system reveals its true scale, because its border is not a planet. The heliopause sits near 120 astronomical units, where the solar wind yields to interstellar pressure. The solar wind is a thin stream of charged particles, and it carries the sun's magnetic field outward like a vast, invisible flag. Far from home, that stream slows and compresses, meeting the tenuous gas between stars. At light speed, that is roughly 16 to 17 hours, still less than a day. Even our star's bubble is not a wall, only a balance point, an ever-shifting frontier shaped by motion through the galaxy. Beyond it, the light changes character in a way cameras can almost suggest. The sun becomes an intensely bright star rather than a sky-filling disk, and the planets lose their reflected glow. The space between stars is not empty, but it is close enough to empty that intuition fails. A few atoms per cubic centimeter can still shape a boundary when the distances are vast. The heliosphere is a kind of a weather system, and the heliopause is its pressure line. Keep going, and the Oort cloud becomes the first real test of patience. Its inner reaches are thousands of AU, and its outer reaches may be tens of thousands. It is not a neat shell, but a statistical swarm, comets on long, slow orbits, loosely held by the sun's gravity. At light speed, the trip becomes days, then weeks, depending on where you draw the line. Out here, a single object can take millions of years to complete one orbit. The edge keeps moving because our definitions keep moving. This is the chapter's rhythm. Each step feels like approaching an end, yet every end becomes a neighborhood. The farther we go, the more the universe insists that scale is the story. The mind keeps reaching for a final boundary, and the cosmos keeps offering another layer. What feels like a conclusion becomes a preface, and the darkness ahead stays stubbornly open. Beyond the heliosphere, the sun's just one star among many, and the next one is not next door. Proxima Centauri is 4.24 light years away, so light takes more than 4 years to arrive. In a night sky view, it is not a dramatic beacon, but a faint red point in a crowded field. That faintness is part of the lesson. Distance dims and dimming hides. A spacecraft would need tens of thousands of years with today's speeds. Even our fastest probes crawl by cosmic standards because chemical rockets are powerful, but not remotely relativistic. The speed of light limit turns interstellar travel into a different kind of problem. That limit is not a technical hurdle, it is a law of causality. In Einstein's relativity, light in vacuum is the same speed for every observer, and that invariance locks the universe's rules in place. No signal can outrun light in vacuum, so no message can arrive before its own light. Distance becomes time, and time becomes a boundary on what can ever be known. We can travel, but we cannot cheat the universe's clock. The deeper implication is unsettling. Some events will always be too far, in a very literal sense. Now the twist that changes everything. When we look outward, we are not seeing space as it is now. We are seeing space as it was when the light began its journey, and the delay grows with every step. The moon is 1.3 seconds ago, and the sun is 8 minutes ago, and Proxima is more than 4 years ago. Even the stars above the horizon are a layered collage of different times. The night sky is not a single moment, but a stitched panorama of delayed arrivals. Scale up, and the time machine becomes obvious. The Milky Way is about 100,000 light years across, so its far side is seen 100,000 years in the past. That is not an abstract number, because 100,000 years is longer than recorded human history. Our galaxy is not a snapshot, it is a layered record. Dust lanes, star clouds, and spiral arms are seen at different ages depending on where they sit. Even within one object, the present is smeared across time. The Milky Way itself becomes more vivid when you remember what it contains. Hundreds of billions of stars orbit a common center, and much of the mass is not luminous at all. Gas and dust form cold nurseries where new stars ignite, while older stars drift in thicker populations. When we look toward the galactic center, we peer through crowded fields and absorbing dust, and the view is both rich and incomplete. The galaxy is a city seen through fog, bright windows, dark alleys, and a hidden architecture of gravity. Step outside the Milky Way, and the past deepens fast. Andromeda is about 2.5 million light years away, so we see it as it was 2.5 million years ago. On screen, it can appear as a pale, tilted spindle with a bright core and faint outer haze. That haze is not emptiness, but a halo of stars and dark matter extending far beyond the visible disk. The local group is a small community, but it already forces cosmic thinking. We are watching neighbors through a thickening time delay. The local group is not a tidy cluster, but a gravitational conversation. The Milky Way and Andromeda dominate, with smaller galaxies orbiting like attendants. Some of those dwarfs are distorted by tides, stretched into streams that wrap their hosts. The shapes we see are clues to past encounters because gravity leaves scars. When we say group, we mean a region where gravity has overcome expansion locally, binding galaxies into a shared fate. Then come clusters and superclusters, where the map becomes web-like. The Virgo cluster anchors our region tens of millions of light years away. In images, it is not one object, but a swarm, elliptical galaxies, like smooth embers, spirals like pinwheels, and faint smudges that only long exposure reveals. Laniakea is the larger basin of attraction that includes Virgo and many other groups. These names are not just labels, they are hints that gravity organizes galaxies into vast structures. Matter flows along filaments, and the voids between them are not nothing but underdense expanses. At this point, we need a method because distance is no longer obvious. We cannot stretch a tape measure across intergalactic space, and we cannot rely on looks far as a scientific category. The eye is easily fooled when brightness and size both change with distance. We build a ladder, rung by rung, each step calibrated by the one beneath. This is the cosmic distance ladder, and it is how we turn faint light into measured scale. It is also a story of careful cross-checks, because each rung inherits the uncertainties below it. The first rung is radar ranging inside the solar system. We bounce signals off the moon, Venus, and asteroids, and time the return. Because the speed of light is known, the travel time becomes a direct distance, with no need for assumptions about brightness. This gives absolute distances in kilometers and AU, tied directly to the speed of light. It is the cleanest geometry we have, and it anchors everything else. In practice, it also refined planetary ephemerides, turning celestial motion into precise prediction. The next rung is parallax, the shift of a nearby star against distant background as Earth orbits the Sun. The baseline is 2 astronomical units across. From one side of Earth's orbit to the other, measure the tiny angle, and geometry gives distance, as surely as a surveyor's triangle. Parallax works well for nearby stars, and missions like Gaia make it precise. Gaia's measurements reach micro-arcsecond precision, a level that turns the sky into a calibrated grid. But the angles shrink with distance, and the method runs out. Eventually, the shift becomes smaller than the instrument's ability to separate it from noise. To go farther, we use stars that change brightness in predictable ways. Cepheid variables pulse with a period linked to their true luminosity because their outer layers expand and contract in a stable rhythm. The physics is a balance between gravity pulling inward and pressure pushing outward, with opacity acting like a valve. Measure the period, infer the luminosity, compare with apparent brightness, and distance follows. Henrietta Leavitt's period, luminosity relation, turns flicker into a ruler. Her work, done with painstaking attention to photographic plates, became one of astronomy's most powerful calibrations. Cepheids reach into nearby galaxies, but not to the deep universe. For that, we use type Ia supernovae, explosions with consistent peak brightness after standardization. They begin in binary systems where a white dwarf accumulates matter until a runaway thermonuclear reaction disrupts it. The details are complex, yet the outcome is remarkably uniform, which is why they can serve as standardizable candles. They are bright enough to be seen across billions of light years. They extend the ladder and reveal how expansion has changed over time. They also carry a warning because calibration errors echo upward through every rung. Even dust in a host galaxy can mimic distance by dimming light, so astronomers must correct carefully. Beyond individual candles, we lean on the universe's overall pattern. Galaxies have spectra with recognizable lines, fingerprints of elements like hydrogen and calcium. Those lines shift toward red with distance, sliding to longer wavelengths in a way we can measure precisely. Measure the redshift and we can estimate distance through the Hubble-Lemaitre relation. Edwin Hubble's observations built the empirical law, and Georges Lemaitre's earlier work framed the expanding interpretation. This is not a simple ruler because it depends on cosmic history. The same redshift can correspond to different distances under different expansion models. Redshift needs careful language because it hides two different ideas. A Doppler redshift comes from motion through space, like a siren changing pitch. A cosmological redshift comes from space itself, stretching while light travels. The wavelength is pulled longer because the path is expanding under it. In plain terms, the light is not merely chasing a receding object. It is being carried on an enlarging stage. That distinction matters more and more as we look farther back. This is where our intuition breaks and the documentary's tension grows. Galaxies are not shrapnel flying into pre-existing emptiness, with a single explosion pushing them outward. On large scales, they ride the expansion of the metric, embedded in space as it stretches. The mathematics describes changing distances between co-moving points, not a central blast into surrounding void. The farther we look, the stranger the motion becomes, because expansion accumulates over time. The light has been traveling while the map itself has been subtly redrawn. In the nearby universe, Doppler language can be a useful approximation. In the distant universe, cosmological redshift dominates, and recession speed is not like a rocket speed. It is a rate of separation driven by expanding space, and that rate depends on time. That separation can exceed the speed of light without violating relativity, because no object locally outruns light. Relativity forbids faster than light motion through local space, not the growth of space between far separated regions. The result feels like a loophole, yet it is simply the universe honoring its own definitions. So the edge is not a cliff you approach with engines. It is a horizon you approach with photons, because photons are the messengers that define what we can observe. Every extra billion light years is also an extra billion years of look-back time. The universe is teaching us that far and long are the same word. When we push the camera deeper, we are not just zooming out, we are rewinding. Now we turn the ladder into a narrative of aging. Nearby galaxies look mature, with settled structures and older stars that glow warmer and redder. Farther galaxies look smaller and more irregular because we see them earlier in their assembly. Some appear as clumpy chains, bright knots of star formation stitched together by gravity. Their light is often dominated by hot massive stars that burn fast and die young. Push far enough and galaxies thin out, because there was a time before galaxies existed. the sky begins to lose familiar shapes, and the scene becomes more primordial. This is the approach to a shoreline, and it is not made of rock. It is made of the universe's early conditions, when matter and radiation were coupled. Before a certain epoch, the universe was a hot plasma that scattered light constantly. Electrons and atomic nuclei moved freely, and photons could not travel far without being deflected. In that state, space was filled with a bright fog, and seeing meant only a short-range blur. Photons could not travel freely, so the cosmos was opaque. We are not naming that wall fully yet, but we can feel it ahead. The farther we look, the closer we get to the moment when the first long-distance light was released. The view narrows not because space ends, but because transparency begins at a finite time. The universe has an age, and that age bounds our sight. There is a last scattering of light beyond which ordinary vision cannot pass, no matter how perfect the telescope. Expansion makes this boundary more subtle. The observable universe is larger than the naive light travel distance, because space expanded while light was en route. The most distant light we see today started much closer than its source's current distance. In other words, the photon's journey was not across a fixed stage, but across a stretching one. Our cosmic maps are drawn on a moving surface. Even the word distance becomes a choice of definition, depending on how you slice time. This is why the word edge keeps shifting. If we ask for the farthest place we can see, we get one answer, defined by light and time. If we ask for the farthest place that can ever affect us, we get another answer, defined by expansion and causality. These are not philosophical games. They are physical categories with measurable consequences. The universe offers multiple horizons, each with its own meaning. One is about what has already reached us, and another is about whatever can. The distance ladder, the speed limit, and the look-back effect now locked together. We measure distances by light's behavior, but light is altered by expansion. We infer motion from redshift, but redshift is also a record of cosmic stretching. We search for an edge in space, and we keep finding edges in time. The deeper we look, the more the universe answers with history rather than geography. So, we return to the central question with sharper tools. Does the universe have an edge, and what lies beyond it? The chapter's answer is not yet a verdict, but a reframing. The most immediate edge is not a place you can travel to, because travel is trapped by light speed. Even if you could accelerate forever, the universe would still ration what you can influence and what can influence you. If the universe has an edge, it might not be a place you can travel to. It might be a time you can only see. And as we approach that time, the next chapter begins. Because horizons are not metaphors, they are physical limits on connection, written into the universe's history. The question becomes less, where is the wall? And more, which signals are still able to arrive? We have moved from Earth's fading air to the cosmic shoreline of visibility. The edge keeps moving because the universe is not only large, it is also old, expanding, and unwilling to reveal what light has not had time to carry. Now we follow the horizon itself and ask what it allows and what it forbids. And in that narrowing band of reachable information, we begin to see the shape of the universe's past. We have been chasing an edge through distance, and distance keeps turning into time, because in cosmology, the ruler is always a clock. The first true cosmic edge is not a rim of matter, and it is not a cliff where galaxies stop. It is the observable universe, defined by which light and which information has had time to reach us. The observable universe is not the whole universe. It is the region from which signals could have arrived since the Big Bang, given the universe's finite age and light's finite speed. That definition sounds almost intuitive until expansion enters, because space did not hold still while the light traveled. In everyday life, a journey happens through a fixed landscape, but the cosmos changes its scale while the traveler is in flight. If the universe were static, the radius would be about 13.8 billion light years, matching the age and light travel distance. Yet the universe expanded during every photon's journey, stretching the path under the traveler and diluting the energy it carried. The result is a present-day radius of about 46.5 billion light years, even though the oldest light has been traveling for 13.8 billion years. That number is not a trick of units. It is a record of how much the universe grew while the message was en route. This is the first lesson of the chapter, and it is easy to miss if you picture space as a stage. The edge we can see is not where the light started. It is where that source is now, after billions of years of expansion that steadily increased the separation between us and it. When astronomers say distance in this context, they often mean a distance defined on a cosmic time slice, an accounting that respects the universe's growth. Cosmologists give this limit a name that sounds like geography, even though it is not a place. It is the particle horizon, the maximum distance from which any signal could have reached us up to this moment. It is a boundary made of time, drawn by the universe's age and the speed limit of information. It is also a boundary made of causality, of what could, even in principle, have had an effect here. Imagine standing in a foggy field with a lantern, knowing you can only walk for an hour. The fog is not a wall, and the field may extend forever, but your reachable region still has an edge. Your boundary is set by how long you have had to move and how far your light can travel, even if the landscape continues beyond sight. The particle horizon works the same way, except the fog is cosmic history, and the walking time is the age of the universe. The lantern's glow is every messenger we can receive, photons, particles, and ripples in space-time. The eerie part is that this horizon is not fixed, and it never was. As time passes, more light has time to arrive and the particle horizon grows, slowly adding new shells of the past to our accessible record. Yet, the growth does not mean we will eventually see everything, because the universe's expansion has its own tempo. Some distances open up faster than information can cross them, and that changes what eventually can mean. To see why, it helps to picture a simple animation, a grid drawn on rubber with dots for galaxies, stretching outward as time advances. A photon leaves a distant dot and heads toward the center, but the grid expands beneath it, lengthening the remaining route. The photon still moves at light speed locally, yet the overall separation it must overcome can grow while it travels. In that visual, the observable universe is not a circle traced by a beam. It is a circle traced by a beam on a surface that keeps swelling. Now we introduce the second horizon, and it points in the opposite direction. The cosmic event horizon is the limit beyond which events will never influence us, even with infinite waiting. It is not about what has reached us already. It is about what can ever reach us in the future, no matter how patient we are or how long the cosmos survives. The event horizon exists because expansion is not merely continuing like a steady wind. It is accelerating, and that acceleration changes the causal map of the cosmos. Regions far enough away recede in a way that makes their future signals forever unable to cross the widening gap. In practical terms, there are places whose light is on its way now, and places whose light will never arrive, because the space between us and them grows too quickly. This is where dark energy enters the story, quietly but decisively. We do not unpack its nature yet, and we do not pretend we have a final answer for what it is. We note its effect, because the effect is measurable, and it is written into the sky. It drives accelerated expansion, and accelerated expansion creates a permanent horizon of influence, an edge that is not about our instruments, but about the universe's dynamics. So we have two edges that are not walls, and they do not coincide. The particle horizon marks the farthest past signal that could have arrived by now given the universe's age. The event horizon marks the farthest future event that can ever affect us, given the universe's acceleration. One horizon expands with time because more history becomes visible. The other can lock parts of the universe out of contact forever, because acceleration turns distance into isolation. These horizons reshape our central question. If the universe has an edge, it may be an edge of evidence, not an edge of space. Beyond the observable universe could be more galaxies, more structure, more of the same physical laws, repeating across vast scales. But beyond the event horizon could be regions that are real and forever unreachable, not by engines and not even by light. The cosmos can contain more than it can ever reveal to us. To feel what this means, we need the deepest light we actually observe, the oldest image our telescopes can assemble. That light is not from the first stars and not from the first galaxies. It is older than any structure, and it arrives from every direction with almost perfect uniformity, as if the universe itself remembers a time before it had landmarks. The cosmic microwave background is the afterglow of an earlier universe, and its discovery in the 20th century helped cement the Big Bang model. It is often described as a surface, but it is really a time, an epoch that appears as a sphere around us, because we look back along our past light cone. Wherever we look, we see the universe. At the moment it first became transparent to ordinary electromagnetic radiation. In that sense, the CMB is less like a wall in space and more like a timestamp painted across the sky. Early on, the universe was a hot plasma of electrons, protons, and light. Photons scattered constantly off free electrons through a well-understood process, and they could not travel far without being redirected. In that state, the universe was opaque, like a bright, dense fog where distance vision is impossible. The light did not disappear. It was trapped in a restless thermal crowd, exchanging energy and direction millions of times. As the universe expanded, it cooled, and cooling changed what matter could do. About 380,000 years after the Big Bang, Conditions shifted enough for electrons and protons to combine into neutral hydrogen. This is recombination, and the name is historical. There was no earlier combination in our universe's timeline, but the physics resembles recombining charges in a laboratory plasma. It matters because neutral atoms scatter photons far less efficiently than free electrons, so the fog thinned abruptly. When electrons were captured into atoms, photons decoupled from matter and began to stream freely through space. Those photons have been traveling ever since, stretched by expansion from visible and infrared energies down into microwaves. We see them today as the cosmic microwave background with a measured temperature of about 2.725 Kelvin. That temperature is not just a number. It is a thermometer reading for the whole universe, cooled and diluted by expansion over nearly 14 billion years. The CMB is called the surface of last scattering because it marks the last time most photons were scattered before reaching us. It is the farthest electromagnetic light we can see directly, not because nothing existed earlier, but because earlier light could not propagate freely. The CMB is a relic boundary in time, and it functions like a light wall. Behind it, the universe is not empty. It is simply unreadable in ordinary light. Visually, the CMB is almost featureless at first glance, a smooth bath of microwave glow that fills every direction. Then the data are processed, the contrast is boosted, and a hidden texture appears, tiny warm and cool patches scattered across the sphere. Those patches are not artifacts of our detectors. They are the universe's earliest accessible fingerprints, preserved because the photons have been free streaming since recombination, yet the wall is not perfectly smooth, and the imperfections are the point. The CMB has tiny temperature anisotropies at the level of about 1 part in 100,000, around 10^5. In plain terms, the early universe was astonishingly uniform, but not perfectly so. Those small variations correspond to slight differences in density and gravitational potential, and gravity later amplified them into galaxies, clusters in the cosmic web. In this chapter's logic, the CMB does 2 jobs at once, and both are essential. It is a limit on direct electromagnetic observation because it is the earliest light that can reach us without being scrambled. It is also a map of initial conditions, a fossil pattern that lets us infer what the universe was like before stars existed. When cosmologists fit models to the CMB's angular pattern, they are reading a coded message about the universe's contents and geometry. But even after recombination, the universe did not become instantly bright to our telescopes, because transparency is not the same as illumination. There was a long interval with no stars, no galaxies, and no new visible light sources. This is the cosmic dark ages, when neutral hydrogen filled space and structure was still assembling under gravity's slow pull. The universe was clear, but it was dim, like a room with clean air and no lamps. Eventually, the first stars formed, and their ultraviolet radiation began to change the universe again. That radiation reionized hydrogen, stripping electrons back off atoms and making the intergalactic medium ionized once more. This epoch of ionization is not a return to the original plasma, because the density was far lower and the conditions were different. Still, it is a major phase change in the cosmic story, and it marks the universe's transition from darkness to a landscape lit by astrophysical sources. Reionization matters for what we can see because it marks the rise of the first luminous structures, the earliest beacons that telescopes can chase directly. It also reminds us that visible light is a late messenger, arriving only after gravity built stars capable of shining. Stars must exist before starlight can carry information, and stars did not exist near the beginning. When we look to extreme distances, we are also looking to times when the universe had not yet invented the familiar kind of light. So when we ask what lies beyond the observable universe, we also ask what lies before our earliest light. The CMB is not the beginning of the universe. It is the earliest electromagnetic snapshot that can reach us without being erased by scattering. It is a horizon, not because reality stops there, but because the medium before it was a kind of cosmic blur. Opacity before recombination is the key constraint, and it is rooted in basic plasma physics. In the hot plasma, photons were trapped in a constant exchange with charged particles, scattering so often that any directional image was destroyed. The mean free path of a photon was tiny compared with cosmic distances, so light behaved like diffusion rather than travel. No telescope can see through that era using ordinary light because the medium itself prevented long-range photon flight. This is where the story opens a narrow door to other messengers. And the door matters because it respects the same logic of horizons. Light is not the only carrier of information, and the universe produced signals that decoupled earlier than the CMB. If we can detect them, they could let us probe times that electromagnetic radiation cannot reveal. The question becomes not only how far we can see, but which kinds of evidence can survive the early universe. One candidate is the cosmic neutrino background. Neutrinos interact extremely weakly, so they decouple much earlier than photons, roughly about 1 second after the Big Bang. In principle, they carry information from a younger universe than the CMB can show, from an era when the cosmos was still a furnace of particle reactions. They would be everywhere, streaming through us constantly, almost indifferent to matter, yet their very elusiveness is what makes them valuable. Another candidate is primordial gravitational waves, ripples in space-time itself. Some models predict these waves were generated in the early universe, possibly during inflation, and they would pass through plasma without being scattered like photons. If detected, they would be a direct probe of physics at energies far beyond any laboratory. They would also be a test of ideas about the universe's earliest moments, when expansion may have been extraordinarily rapid. But these messengers come with a hard truth, and the truth is not philosophical, but experimental. Their detection is extraordinarily difficult because neutrinos are elusive and primordial gravitational wave signals are faint and easily confused with later sources. Even when we know what to look for, the universe is noisy and our instruments have limits. The promise is profound, but the evidence is demanding, and the boundary between speculation and measurement is part of the drama. Even without those detections, the observable universe already forces a shift in how we talk about edges. The boundary we meet is not a border of space, but a border of evidence. It is the limit of what can be verified by signals that have actually arrived. been recorded, and been checked against competing explanations. In a universe governed by finite signal speed, knowledge has a geometry. That limit does not imply a physical end, and it does not even imply special location. The universe could extend far beyond 46.5 billion light years in every direction, with more galaxies than we can count and more volume than we can imagine. Could be finite, but larger than our horizon, curved in a way that hides its full shape from any one observer. It could be infinite, with our observable region a small patch of an unending expanse, repeating the same physics in distant places we will never sample. The unsettling part is that beyond the particle horizon, there may be regions with galaxies and histories like ours, following the same laws and building the same kinds of structures. Or there may be conditions that differ in ways we cannot test, because no signal from there can reach us yet. The boundary is not a statement about what exists. It is a statement about what can be known from here, now, under the rules of causality. Expansion deepens the mystery by separating existence from access, and it does so with mathematical precision. Some regions are outside our current view, but could enter it given enough time, as the particle horizon grows and more ancient light finally arrives. Other regions are outside our event horizon, and their future is causally disconnected from ours forever. Even if the universe lasts without end, the cosmos can be larger than our future, not just larger than our present. So the observable universe is an edge that moves and an edge that divides. It moves because time passes and light arrives, steadily adding new information to the record. It divides because accelerated expansion can permanently isolate parts of reality, turning distance into a one-way separation. The same expansion that reveals the past can also seal off the future. This chapter returns to the opening hook in a new form, and the sky becomes a diagram of limits. At the top of the sky, where blue thins into black, the question is not only how far we can go. The question is whether far is a meaningful category when information itself has horizons. When we say out there, do we mean a place we could reach, or only a place we can never influence? We can map what we can see with exquisite precision and still face a larger unknown that is not merely ignorance but inaccessibility. Beyond our view may be more of the same, repeating patterns across unimaginable distances, with no boundary and no center. Or beyond our view may be something we cannot ever verify directly, because the universe's expansion makes contact impossible. The difference between those possibilities is not visible in a photograph, and that is part of the unease. This is the narrative tension we carry forward. We have reached a boundary that is not a border of space, but a border of evidence. The edge is real in its consequences, yet it refuses to behave like a wall. It is an edge you can define, calculate, and measure, yet you cannot touch it, and you cannot cross it in the way your intuition expects. Now the next question becomes unavoidable, because horizons describe what we can learn, not what space is. If the observable edge is about what we can see, then what is space itself like? Is the cosmos finite or infinite? Is it curved or flat? And if geometry can hide an end, then the universe's true size may be a question that horizons will never let us settle completely. We leave the observable universe not by crossing it, but by interrogating the stage it sits on, and by asking what kind of arena could produce such limits. The next chapter turns from horizons to geometry and asks whether space can be bounded without having an edge. We left the observable universe with a new kind of edge drawn by light and time. Now we ask what the stage itself looks like, especially where no signal can guide us. The question is almost unfair because our best instruments are made of light, and light carries its own limits. Yet cosmology keeps pushing because geometry can be inferred even when it cannot be directly seen. General relativity gives one clear thread that ties matter to geometry. Mass and energy tell space-time how to curve, and that curvature tells matter and light how to move. Einstein's field equations compress that idea into a single relationship, linking the stress energy of the cosmos to the shape of space-time itself. It is a theory of gravity, but it is also a theory of measurement, of what distance and time mean when the universe is not flat. In everyday life, gravity feels like a force pulling objects together. In Einstein's picture, free fall is motion along the straightest possible paths in curved space-time, even when those paths look bent to us. Those paths are called geodesics, and they replace the idea of invisible tugging with rule about geometry. A satellite in orbit is not held by a tether of force. It is following a geodesic through curved space-time, continuously falling around Earth. This is not only a local story around planets and stars. In cosmology, the same equations describe the whole universe's large-scale shape, and they do it without privileging any center. We treat the cosmos as homogeneous and isotropic on the biggest scales because surveys show statistical smoothness when we average over hundreds of millions of light years. Galaxies cluster into filaments and walls, but from far enough away, the pattern blurs into a uniform fog. That assumption is not a claim that the universe is simple. It is a disciplined simplification backed by maps of galaxies and by the near uniform glow of the cosmic microwave background. With it, geometry becomes a single evolving scale factor, AT, that tells us how distances between co-moving points change with time. The focal W metric encodes expansion and the possible curvature of space, and it is the simplest stage that still matches what we observe. It is, in a sense, the universe's most economical blueprint. The central question returns in a new form. Does the universe have an edge, or can geometry hide an ending without any boundary? If space has a limit, is it like a wall, or is it like the end of a loop that never presents a rim? The language of edge belongs to surfaces and maps, but the universe may not cooperate with our metaphors. Curvature is the first fork in the road. There are three broad cases that describe the spatial geometry at a given cosmic time, and they are defined by the sign of curvature. Positive curvature is closed, zero curvature is flat, and negative curvature is open. These are not just labels of shape, they are different rules for how volumes and angles behave as you move outward. We reach for analogies because our brains are trained on surfaces. A sphere's surface has positive curvature, and it bulges in a way that makes straight lines eventually meet. A plane has zero curvature, and its geometry matches the grid we draw on paper. A saddle has negative curvature and it flares outward so that nearby lines diverge. These analogies are useful and also misleading. They are two-dimensional surfaces embedded in a higher space we can picture, and that extra direction makes the bending feel intuitive. Our universe's space is three-dimensional, and it does not need an external direction to bend into. Curvature can be intrinsic, meaning it is detectable by measurements made entirely within the space. Positive curvature in 3 dimensions is like a 3-sphere, a closed space with no boundary. Flat space is Euclidean, the geometry of ordinary intuition, where the shortest path between 2 points is the familiar straight line. Negative curvature is hyperbolic, where parallel lines diverge and volumes grow faster than you expect. In hyperbolic space, there is more room than Euclid would predict, and that surplus shows up in how quickly spheres of increasing radius gain volume. Curvature is not about the universe being curved into something else. It is about the internal rules of distance and angles, the bookkeeping of geometry from the inside. It is about how triangles add up, how circles scale, and how light rays converge or spread as they travel. On a positively curved surface, the angles of a triangle sum to more than 180 degrees, while in negative curvature, they sum to less. That is a plain language test, even if we cannot draw the triangle on a cosmic chalkboard. In a closed universe, the idea of an edge changes completely. You could travel in one direction forever and never hit a wall, yet the total volume could still be finite. The phrase that sounds like a paradox, finite but unbounded, becomes a precise geometric statement. There is an end to total size, but no boundary where space stops, so there is no rim to fall from. On a sphere, you can walk endlessly without finding a cliff. The surface is limited in area, but it has no borderline, and every direction is forward without ever meeting an edge. A closed 3-dimensional space generalizes that idea, even though we cannot visualize it directly. If you try to imagine it, the mind reaches for a higher dimension, but the mathematics does not require one. If that were our universe, the search for an edge becomes a search for repetition. A traveler might eventually return to the starting region from the other side, not by turning around, but by continuing straight. The cosmos would be self-contained, with distance looping back on itself, and the farthest journey would be a kind of long return. What would it mean then to say beyond, if beyond is only elsewhere in the same space? An open universe is the opposite intuition. Negative curvature suggests infinite extent, with space spreading outward without closure, and with geodesics that separate faster than they would in flat geometry. Flat space can also be infinite, stretching without end in every direction, and our everyday sense of endlessness fits it easily. But that ease is a psychological comfort, not a proof. Curvature alone does not settle finiteness. Geometry describes local shape, yet topology describes global connectedness, and the two can be surprisingly independent. Two spaces can share the same local curvature and still differ in how they wrap, like two maps drawn with the same grid, but glued into different forms. A universe can be locally ordinary and globally strange. Topology is the second fork, and it is quieter, but more unsettling. It asks whether space is simply connected or whether it is multiply connected, with identifications that fold distant points together. It asks whether a straight path can thread a shortcut through the universe's own stitching. In topology, the drama is not in bending, but in the hidden rules of adjacency. Even a flat universe can be finite if it wraps like a 3 torus. In that picture, going far enough in one direction brings you back, not by curving your path, but because space itself is stitched. The local rules stay Euclidean, so triangles still add to 180 degrees in small neighborhoods, yet the global map closes. It is the difference between the texture of a fabric and the way that fabric is sewn. The simplest analogy is a video game world that tiles walk off the right edge of the screen and reappear on the left, and the player experiences continuity without ever seeing a boundary. The world feels endless to the player, yet its underlying domain is finite, and the repetition is built into the code. In a cosmic version, the code is geometry and topology, and the screen edge is not a wall, but an identification. In 3 dimensions, the tiling is harder to picture, but the concept is the same. Space could identify opposite faces of a cube, turning a finite region into a boundary-free cosmos, and every exit would be an entrance from the other side. No wall is required, because the wall is replaced by equivalence, a rule that says 2 distant-looking locations are actually the same. The universe would be like a room where every door leads back inside. If space wraps, the central question becomes a kind of illusion test. The edge we imagine might be only a limit of our map, a cartographic boundary mistaken for a physical one. Beyond the edge would be the same space, reached again, and the feeling of outside would dissolve. The universe would not end, it would repeat. General relativity links these possibilities to matter content. The Friedman equations connect expansion rate, energy density, pressure, and curvature, and they do it in a way that turns cosmic history into a measurable story. Curvature is not chosen by taste, and it is not an aesthetic preference for closed or open. It is constrained by what the universe contains and by how that content dilutes as space expands. Cosmologists package that link into a single parameter. The density parameter, omega, compares the actual total density to the critical density, and the critical density is the value that makes spatial curvature exactly 0 in the simplest models. It is defined by the Hubble expansion rate, so it is not a fixed cosmic constant, but a time-dependent benchmark. Omega is a ratio, but it carries a deep implication about the universe's global shape. If omega is greater than 1, the universe tends toward positive curvature. If omega equals 1, the geometry is flat, at least in the idealized FLRW description. If omega is less than 1, the geometry tends toward negative curvature. This sounds like a clean classification, but the universe complicates it in ways that matter for interpretation. Omega includes matter, radiation, and dark energy, each evolving differently with expansion. Matter density falls as volume grows. Radiation falls even faster because each photon is redshifted, and dark energy can remain nearly constant if it behaves like a cosmological constant. Curvature behaves like its own effective component, and its relative importance changes with time. The upshot is simple. The same present-day omega can emerge from different early histories, so we do not infer curvature from a single number measured once. We infer it by fitting a whole model to multiple data sets, each sensitive to geometry in a different way. The most famous of those data sets is the cosmic microwave background, a relic light that carries an image of the universe when it was only about 380,000 years old. It is not merely a picture, it is a calibrated experiment performed by nature. The CMB is not only a horizon in time, it is also a ruler imprinted on the sky, because the early plasma supported sound waves, and those waves left a preferred physical scale. In that hot, ionized fog, photons and baryons were tightly coupled, and pressure fought gravity in a rhythmic contest. The largest distance those sound waves could travel before recombination sets a standard length. That scale is called the sound horizon, and it is known from early universe physics. When we observe it today, it appears as a characteristic angular size in the CMB's acoustic peaks, a pattern of hot and cold spots with a statistical regularity. Curvature changes the apparent angle by changing the geometry of light paths between us and the last scattering surface. The physics sets the ruler, and geometry sets how big it looks. Positive curvature makes a given physical scale look larger on the sky because light rays converge and the surface of last scattering is effectively closer in angular terms. Negative curvature makes it look smaller because geodesics diverge and the same ruler subtends a tighter angle. Flat geometry sits between them, matching a specific angular pattern that can be read from the spacing of the peaks. This is why the CMB is so powerful. It turns the sky into a geometry test. Measurements from missions like WMAP and Planck show the peaks where flatness predicts within tight uncertainties. The result is not perfect certainty because every measurement has systematics and every model has assumptions, but it is a strong constraint. The universe is very close to flat, with omega near 1, and the allowed deviation is small. In many fits, the curvature parameter is consistent with 0 at the level of a few parts in 1,000. Near 1 is the phrase that keeps the mystery alive. It does not prove exact flatness, and it does not guarantee infinite extent. It says any curvature radius is very large compared to the observable universe, so large that our horizon may be sampling only a tiny patch. We could be living on a vast 3-sphere and still see a sky that looks almost Euclidean. That means a closed universe could still be real and still be finite. It would just be so large that our horizon samples only a small patch, like standing on Earth and mistaking the ground for a plane. The analogy is more than poetic because Earth's curvature is measurable only when you compare distant points with careful instruments. In the same way, cosmic curvature reveals itself only when you measure across the biggest baselines available. The same is true for a wrapped topology. A 3 torus could exist with a fundamental domain larger than what we can see, and the tiling would be hidden beyond our observational reach. If the wrap length exceeds our horizon, the universe would look ordinary and unwrapped from here. The cosmos could be globally compact, while locally indistinguishable from infinite space. So, the search becomes practical and specific. If space wraps within the observable volume, it should leave signatures, because light would have multiple routes to reach us from the same region. The sky would contain repeated patterns, and repetition would be the fingerprint of identification. The universe would behave like a hall of mirrors, but with physics instead of glass. The cleanest proposed signature is matched circles in the CMB if the last scattering surface intersects itself due to wrapping. We would see pairs of circles with the same temperature fluctuations, like identical rings stamped onto different parts of the sky. The circles would appear in different directions, but share the same pattern because they would be two views of the same physical circle in space. It is a geometric prediction that does not depend on the details of galaxies or stars. This is a sharp prediction, and it turns topology into an observational question. Teams have searched CMB maps for these correlations, scanning for circle pairs across many radii and orientations. The computation is demanding because the parameter space is large and the signal can be subtle. Still, the logic is clean. If the universe is small enough, the circles should be there. The search is hard for reasons that are not excuses, but physics and data realities. Foreground emission from our galaxy contaminates the microwave sky, especially along the Milky Way's bright plane, and removing it is an art as well as a science. Instrument noise adds randomness, and beam effects smear small features. Cosmic variance limits precision because we have only one universe to sample, so the largest scale patterns have unavoidable statistical uncertainty. Even if the signal exists, it can be blurred. Reionization and gravitational lensing slightly distort the CMB pattern, bending photon paths and mixing angular scales. The last scattering surface has thickness, so the imprint is not infinitely sharp, and that thickness washes out perfect correlations. In practice, topology signatures must compete with the universe's own messy realism. So far, no convincing matched circle detection has survived scrutiny. Non-detection does not prove infinite space, because absence of evidence is not evidence of absence when the universe may be larger than we can test. Instead, it sets a lower bound on the size of any wrapped dimension, pushing it beyond a significant fraction of the observable universe. The hall may still be closed. We may simply be too near the center to hear an echo. Other topology tests chase the same idea in different ways. Large-scale correlations in galaxy surveys can hint at repetition, though structure formation adds complexity and bias, and galaxies are not perfect standard markers. Polarization patterns in the CMB offer another channel, with different systematics and different sensitivity to late-time distortions. Each method is an attempt to turn global geometry into a pattern we can check. Each test shares the same logic. If the universe is small enough to wrap within our horizon, light would have had time to lap the cosmos, arriving along multiple geodesics. We would see duplicates, like echoes in a closed hall, and those echoes would line up in statistically recognizable ways. If we do not see echoes, the hall may still be closed, but it may be larger than our hearing range. This is where the chapter's tension tightens. A finite universe with no boundary would erase the naive edge, replacing the cliff with a loop, and beyond with again. It would be a universe that ends only in the sense that a circle ends, by returning to itself. That idea is philosophically unsettling, because it removes the comfort of an outside. But if space does not wrap within reach, the old question returns in a harsher form. Is the universe infinite in extent, with no closure anywhere, or does it have a different kind of boundary? Not geometric, but physical. Infinity is not a place we can visit, and it is not a measurement we can complete, yet it remains a live possibility. The universe may be finite but huge, or infinite, but observationally indistinguishable from huge. General relativity allows boundaries of several kinds. There can be singularities, where classical space-time description fails, and where curvature becomes so extreme that the equations stop being trustworthy. There can be horizons that block information without ending space, like the event horizon of a black hole or the cosmic horizon of accelerated expansion. There can be regions where our effective laws change, even if geometry continues, and the boundary is then one of physics rather than distance. Yet, this chapter stays with what we can constrain. Curvature is near zero, and topology shows no small-scale wrap, at least within the sensitivity of current data. The universe looks like an enormous, nearly Euclidean expanse across what we can observe, with galaxies scattered like islands in a dark sea. The simplest reading is that space is either very large and slightly curved, or effectively flat on all scales we can test. That near flatness is itself a clue, and it is hard to ignore. In the Friedman framework, exact flatness is unstable under many histories because deviations from omega equals 1 tend to grow with time and matter and radiation-dominated eras. A tiny early deviation would have amplified over billions of years, making today's near one value seem unlikely without explanation. The universe appears to be balanced with suspicious precision. This is the flatness problem, stated without drama, but with real weight. Why should the universe be so close to the critical density after billions of years of expansion, when ordinary evolution would push it away? Why does the cosmic geometry balance on a knife edge, and why does it do so across the entire observable sky? Is it a coincidence or a fossil clue from an earlier phase? One answer is that the balance is not an accident. Inflation proposes an early era of accelerated expansion that stretches space enormously, driven by a high energy state with negative pressure. Stretching drives curvature toward zero, like smoothing wrinkles on a surface by pulling it taut, and it does so rapidly. After enough inflation, any initial curvature becomes diluted, leaving a universe that looks flat to extraordinary precision. Inflation does not merely adjust a parameter, it changes what we mean by beyond, because it can make our observable universe a tiny patch of a much larger whole, one that may extend far past our horizon. It can also generate the primordial fluctuations that later become structure, seeding the pattern that the CMB records as faint temperature variations. In that sense, inflation connects geometry, statistics, and the origin of cosmic structure in a single narrative. If inflation happened, the universe could be far larger than our horizon, perhaps effectively infinite to us. It could also contain regions with different properties, depending on how inflation ends and where the energy converts into matter and radiation. The edge question shifts from geometry to the boundaries of physical domains, where one set of conditions gives way to another. We are still asking about limits, but the limits may be of phase and history rather than of space. So this chapter ends with a pivot. We began by asking whether space has an edge you could reach, a boundary like the end of a road. We found that geometry can remove edges without removing finiteness, and topology can hide closure inside local normality. The universe can be finite and still offer no place where space simply stops. We tested that idea against the sky and found near flatness and no obvious wrap. Now the mystery becomes sharper, not softer, because the data do not close the case. Why is the universe so close to flat? And what happened early on to set that condition? If the cosmos is a shape, it is a shape whose curvature is either vanishingly small or stretched beyond our reach. The next step is not farther outward, but farther back into the first instance. If near flatness is a fossil, inflation may be the event that made it, imprinting its consequences on everything that followed beyond the edge of space, may be hidden in the meaning of beyond itself, whether the universe loops, stretches, or divides into domains we cannot yet see. We rewind past the first atoms, past the first light, toward the first fraction of a second. Temperatures soar beyond any star's core, and energies dwarf anything built on Earth. In this regime, even the vacuum is busy. Quantum fields jitter, virtual particles flicker in and out, and space-time itself becomes an active participant. The visuals should feel almost abstract at first. A dark canvas, then a wash of heat, then a trembling grid that hints at geometry. Let the grid ripple as if it has tension, because at these densities, gravity is not a background force. We are not watching matter fly through space like shrapnel. We are watching the stage expand, while the actors, particles, and fields are still being written into the script. Earlier, we met horizons as edges of evidence, not walls of space. Now we push behind the CMB wall in time, where ordinary light cannot travel freely. Before recombination, photons scatter off free electrons so often that the universe is effectively opaque, like a fog bank made of plasma. Each scattering resets a photon's direction, so information diffuses slowly, even though light itself moves fast. If we want an origin story for geometry and structure, we need physics that works in extremes. The early universe is not just hot, it is dense enough that particle species appear and vanish as temperatures cross their mass thresholds. At these energies, the distinctions between forces may blur, and symmetry breaking can reshape what laws look like at low energy. What feels like separate forces today may have been different faces of a single interaction before the cooling universe split them apart. In that earliest instant, the familiar expansion of space is not the whole story. The standard Big Bang picture expands, cools, and thins, and it does so with remarkable success. It explains why the universe is filled with a nearly uniform bath of microwave photons, and why light elements formed in the first minutes. Hydrogen, helium, and traces of lithium emerge from nuclear reactions that freeze as expansion outruns fusion. Yet when we compare that simple expansion to the sky's uniformity and geometry, puzzles appear. These are not small bookkeeping issues, because they touch the question of why the universe looks so orderly at large scales. They also hint that something dramatic happened before the hot, dense phase we usually call the Big Bang. In this chapter, that before is not a location. It is a different regime, of time and dynamics. The first puzzle is the horizon problem, and it is a problem of causal contact. The CMB temperature is nearly the same in opposite directions to 1 part in 100,000. Those regions look too far apart to have exchanged signals before recombination. Given the finite speed of light, the mismatch is geometric because it comes from tracing light cones through an expanding space-time. In the basic model, the early universe had limited time to communicate because light speed is finite. Separate patches should have cooled to slightly different temperatures, like rooms never connected by air. Yet the CMB looks like it remembers a shared thermostat, as if the entire visible sky once sat in one well-mixed chamber. The eerie part is not uniformity alone, but uniformity across regions that seem never to have been neighbors. To make the tension concrete, imagine drawing circles on the last scattering surface. In a non-inflationary history, widely separated circles never share a past light cone early enough to equilibrate. The universe is expanding, but not fast enough to let distant regions coordinate their temperatures before the fog clears. If you overlay the causal diagram on the sky, the disconnectedness becomes visible as blank space between their histories. The second puzzle is the flatness problem, and it is a problem of cosmic balance. Observations say the density parameter O is very close to 1, meaning spatial curvature is near 0. In ordinary radiation and matter eras, any small deviation from 1 tends to grow. Because curvature becomes dynamically important as the universe expands, the equations do not prefer flatness unless something drives the system there. That makes today's near flatness feel like fine-tuning carried across billions of years. If EO started even slightly off, expansion would have amplified the difference, and curvature would dominate. Instead, the universe sits suspiciously close to the critical line, as though it was set with extraordinary precision at early times. The unsettling implication is that early conditions must have been tuned to many decimal places for the later universe to look ordinary. The mathematics behind this is simple but unforgiving. In the Friedman equations, curvature behaves like a term that dilutes differently than matter or radiation. Unless something drives O toward 1, the universe rapidly diverges from flatness as time runs backward, making early flatness look improbably exact. The closer you push toward the beginning, the more extreme the required precision becomes. The third puzzle is the relic problem, and it is about unwanted leftovers. Many high-energy theories predict heavy relics, like magnetic monopoles, produced in early phase transitions. If they were made abundantly, they should still be around, and we do not see them, despite careful searches in cosmic rays and terrestrial detectors. The absence is informative because it constrains what the early universe could have produced and preserved. Relics are not merely hypothetical clutter, because the early universe is a factory. When temperatures are high enough, reactions run in both directions, and particle species can be produced in thermal equilibrium. As the universe cools, some species freeze out, leaving behind a fossil abundance that can overclose the universe or contradict observations. A relic that is rare by number can still be disastrous by mass, because heavy particles carry enormous energy density. These three puzzles point to the same missing chapter in cosmic history: Something early must have smoothed, flattened, and diluted before the universe became the hot plasma we infer. That missing chapter is called cosmic inflation. Inflation proposes a brief period of accelerated expansion in the very early universe. It is not merely expansion, but expansion that speeds up, so distances grow faster and faster. In general relativity, accelerated expansion requires a form of energy with negative pressure, which sounds exotic but has a precise meaning. It is a statement about the stress energy content of the universe, not a metaphor. Pressure, in Einstein's theory, gravitates along with energy density. Positive pressure adds to gravitational attraction, helping slow expansion. Negative pressure does the opposite. It produces a repulsive gravitational effect on large scales, allowing the expansion rate to accelerate rather than decelerate. In plain terms, the universe can be filled with something that pulls space outward, even as gravity usually pulls inward. A common picture uses a high energy field, often called the inflaton, sitting in a metastable state. While that field dominates, its energy density stays nearly constant as space grows. Constant energy density means the universe does not dilute in the usual way. An expansion accelerates, approaching an exponential growth. The scale factor doubles and doubles again in a rhythm that quickly becomes hard to visualize. Visually, this is the moment the universe outruns itself. A tiny patch becomes enormous, not because matter explodes outward, but because the metric stretches everywhere at once. If you could paint a ruler onto space-time, the tick marks would separate faster than any material signal could travel. The camera should linger on that impossible separation, distance increasing without motion through space. This is where language can mislead, so we draw a clear line. Ordinary expansion can slow down, even while space still grows, because gravity pulls back on the rate. Accelerated expansion means the scale factor's growth rate increases, so the stretching becomes runaway for a time. It is a change in the second derivative of expansion, a subtle idea with enormous consequences. During inflation, the universe outruns itself in a precise sense. Regions that were once close enough to share a common temperature are blown far apart. The uniformity is not created by late communication, but preserved from an earlier, smaller, causally connected patch. Inflation does not make the universe uniform by mixing it. It makes our visible region a magnified sample of something that already equilibrated. Inflation reframes the horizon problem as a timing trick performed by nature. The CMB's opposite sides were once neighbors, able to equilibrate before inflation. Inflation then expands that tiny uniform region to a size large enough to contain our entire observable universe, and the later hot phase inherits that uniformity. What looks like coordination across impossible distances becomes the memory of a time when those distances were small. Inflation also attacks the flatness problem with geometry, not coincidence. Curvature scales away as space is stretched, so any initial bend becomes negligible. After enough accelerated expansion, space looks flat the way Earth's surface looks flat to someone standing in a small field. Local measurements lose sensitivity to global curvature. The longer the stretching, the more the universe is pulled taut. There is a deeper point hiding here. Inflation does not need the universe to begin perfectly flat. It makes flatness an attractor for what we can observe. The longer the accelerated phase lasts, the more any initial curvature is diluted and the more O is driven toward 1. In that sense, inflation turns a fine-tuning worry into a dynamical outcome. The relic problem becomes a dilution story. Any heavy relics produced before inflation are spread across an exponentially larger volume. Their density drops so dramatically that even if they exist, they become effectively absent within our horizon, like a few grains of sand scattered across an entire continent. The universe does not have to forbid relics. It can simply hide them beyond our reach. So inflation is a solution machine, but it must do more than solve puzzles. It must also leave traces that survive to the present, because cosmology demands evidence. The strongest traces are statistical, written into the CMB's tiny anisotropies, where temperature variations map early density differences. In this story, the smoking gun is not a single spot in the sky, but a pattern across the whole sphere. Inflation does not predict a perfectly smooth universe, because quantum physics forbids perfect stillness. Even in a vacuum-like state, fields fluctuate randomly, with uncertainty built into their nature. These fluctuations are not optional noise. They are the minimum restlessness allowed by quantum mechanics. The same uncertainty that limits a particle's position also stirs the inflating field, even when everything looks calm. Inflation takes those microscopic fluctuations and stretches them to astronomical scales. A fluctuation that begins smaller than an atom can be pulled outward until it spans light years. Once stretched beyond the horizon during inflation, it effectively freezes as a classical perturbation in density and curvature, because causal processes can no longer smooth it out. The universe is, in effect, enlarging quantum jitter into a blueprint. Later, when the universe returns to slower expansion, those perturbations re-enter the horizon and begin to evolve. Gravity amplifies overdensities, while radiation pressure resists collapse at early times. The result is a competition between attraction and pressure that leaves a measurable imprint in the pattern of anisotropies. Those imprints carry phase information, which is why the peaks in the CMB spectrum line up so cleanly. This is the seed mechanism for structure formation. Slightly denser regions attract more matter, and gravity amplifies the initial differences. Over billions of years, those tiny contrasts become the cosmic web of galaxies, clusters, and voids, with filaments like luminous threads and empty regions like dark basins. When we map up galaxies today, we are seeing the grown-up version of a faint pattern first sketched in microwaves. The key prediction is not a specific pattern, but a spectrum of fluctuations. Inflation generically produces perturbations that are nearly scale invariant, meaning similar power across many length scales. It also predicts the fluctuations are close to Gaussian, like random noise with a simple statistical character, where rare extremes are truly rare. This statistical simplicity is powerful because it is hard to obtain from complicated late-time processes alone. That nearly matters because the spectrum can have a slight tilt. Different inflation models predict different tilts, and they can also predict subtle departures from perfect Gaussianity. These are the kinds of fingerprints cosmologists hunt for, because they connect a sky map to a physical mechanism. A small deviation can be a clue to the inflatant's potential, the shape of the energy landscape that drove expansion. The CMB lets us test this because it preserves a snapshot of early perturbations. Its angular power spectrum shows acoustic peaks shaped by sound waves in the photon baryon plasma. The overall tilt and amplitude match the inflationary expectation of near-scale invariance within measured uncertainties, and the peak structure matches a universe seeded by coherent primordial perturbations. The data do not just show randomness, they show the right kind of randomness. To picture those peaks, imagine the early universe as a resonant instrument. Gravity tries to compress slightly over dense regions, while radiation pressure pushes back, setting up oscillations. When the CMB is released, we catch those oscillations mid-cycle, frozen into a pattern of hot and cold spots across the sky. The visuals can shift from a sky map to a vibrating membrane, then back again, making the analogy tangible. This is why inflation became the leading paradigm, even without a single definitive smoking gun. It links three classic puzzles to one early mechanism, and it matches the statistical fingerprints we actually observe, yet it remains a framework with many models, not one finished theory, and that openness is both its strength and its vulnerability. The same flexibility that lets inflation fit the universe also forces us to ask which version, if any, nature chose. Historically, inflation emerged in the early 1980s as physicists tried to understand phase transitions in the early universe. The idea evolved quickly from a proposed fix for relics and flatness into a broader explanation for the origin of cosmic structure. That arc matters because it shows inflation was not invented to fit one dataset. It was a response to multiple tensions at once. It also reflects a period when particle physics and cosmology began to merge into a single conversation. The open tests matter because the details can discriminate between models. Inflation can generate not only density perturbations, but also primordial gravitational waves, ripples in space-time produced by the same accelerated expansion. Those waves would leave a specific imprint in the CMB's polarization, adding a new layer to the sky's encoded history. The polarization is like a second channel of information, quieter than temperature, but potentially more revealing. That imprint is called B-mode polarization, a swirling pattern distinct from the gradient-like E modes. Primordial B modes would point to a high energy scale for inflation and would connect our sky to quantum gravity's frontier. Detecting them would be a direct probe of physics far beyond accelerators, because the implied energies can approach grand unification scales. The promise is extraordinary, and that is exactly why the standards of proof must be unforgiving. But the signal is fragile, and the universe adds confusion. Dust grains in our galaxy emit polarized radiation that can mimic B-mode patterns. Separating primordial signal from foregrounds requires multi-frequency maps, careful modeling, and skepticism toward early claims, because the Milky Way sits between us and the cleanest possible view. Even the act of cleaning the data becomes part of the scientific narrative, not a footnote. In visuals, this is where the documentary can slow down and become forensic. We see the CMB polarization map, then the same region in different microwave bands, then a dust template sliding into place. The story becomes one of subtraction and uncertainty. where each improvement in sensitivity also reveals new complexity. The audience should feel the discipline of the process, how confidence is built, not declared. The lesson is methodological, and it echoes earlier chapters about horizons and evidence. Inflation is not accepted because it is dramatic, but because it is testable in principle. The tests are hard because the early universe is faint and the foreground universe is loud, and the difference between them can be smaller than instrumental systematics. In cosmology, the limit is often not imagination, but calibration. Even if B modes are detected, an interpretation will be cautious. Some B modes are produced later by gravitational lensing, which converts E modes into B modes as light is deflected by structure. Untangling primordial waves from lensing and dust becomes part of the story's tension, and it forces cosmology to combine maps, simulations, and statistical inference. The same large-scale structure, seeded by inflation, also becomes a veil we must mathematically peel away. Inflation also connects to the earlier promise of non-electromagnetic messengers. Primordial gravitational waves would be a pre-CMB signal, able to pass through the plasma without scattering. They would extend our evidence horizon closer to the beginning and perhaps toward the moment when quantum physics and gravity collide, where our current theories strain for consistency. If we could read that signal, what would it say about the earliest rules? Were they inevitable or contingent? Yet inflation raises a deeper question about the central theme of edges. If inflation happened, our observable universe may be a tiny patch of a much larger space-time. The edge we chase might be only the boundary of our inflated bubble of visibility, not a boundary of existence. The horizon becomes less like a wall and more like a moving limit on what can ever be verified. In many inflation models, the inflating state ends through a transition, like a field rolling down to a lower energy configuration. When inflation ends, its energy converts into particles and radiation, reheating the universe and setting the stage for the hot Big Bang. Our familiar cosmic history begins after that local ending, with a universe filled with a hot soup of particles that rapidly thermalize. On screen, the abstract grid can flash into a storm of particles, as if the vacuum turns into weather. Reheating is more than a narrative handoff. It is the bridge between an inflationary, vacuum-like phase and the standard thermal history that produces nuclei, atoms, and eventually stars. The details of that bridge, how efficiently energy becomes particles, and which particles appear, can influence later observables without changing the broad outline. Even the abundance of dark matter candidates can depend on this moment, because production mechanisms are sensitive to temperature and timing. But some models suggest inflation does not end everywhere at once. Quantum fluctuations can keep parts of space inflating, even while other regions exit and reheat. This is eternal inflation, and it turns inflation from an event into a process, with endings that occur like local punctuations in an ongoing expansion. The phrase sounds poetic, but the mechanism is technical. Random field kicks can counteract the average roll downward. In eternal inflation, endings happen locally, creating pocket universes, sometimes called bubble universes. Each pocket is a region where inflation has stopped and ordinary expansion begins. The larger space-time continues inflating elsewhere, spawning more pockets over time, so the overall volume in the inflating state can keep growing even as pockets form. The visual language can shift to a dark sea with bright blooms, each bloom a reheated region, each surrounding darkness still stretching. This is not an established fact, and it must be introduced as hypothesis. Eternal inflation depends on the shape of the field's potential and on quantum behavior in curved spacetime. It is plausible within some models, but it is not yet confirmed by direct evidence, and the documentary must keep that distinction crisp. The honest tension is that the mathematics can be compelling even when the observational handle is weak. Still, it sharpens the documentary's mystery because it changes what beyond the edge could mean. Beyond our horizon might be more of our same universe, still governed by the same laws. Beyond that might be other pockets, causally disconnected, with histories that never intersect ours, like islands in an ocean whose surface expands faster than any ship can sail. If no signal can cross between islands, what does it mean to say they share a cosmos at all? To keep the idea precise, we separate levels of multiverse that mean different things. Level Y is the mildest, and it follows from a large or infinite space with the same physics everywhere. Regions beyond our horizon would contain more galaxies and more Hubble volumes, repeating possibilities by sheer scale, even if the underlying laws never change. The repetition is not mystical, it is statistical, the consequence of finite arrangements in a vast arena. Level 2 is stronger, and it is tied to eternal inflation and symmetry breaking. Different bubbles could cool into different vacuum states with different effective constants, particle spectra, or dimensions compactified differently. The laws at the deepest level might be the same, but their low energy outcomes could differ, and that difference would shape what kinds of structures can form. It invites a quiet question. Are the numbers we measure fundamental, or are they local, environmental facts? Evidence is the central difficulty, because causal disconnection blocks straightforward tests. If other bubbles exist beyond our event horizon, their light and gravity may never reach us. The multiverse becomes a claim about what exists, not what we can easily observe, and that tension sits uncomfortably close to philosophy. Cosmology has always lived near that boundary, but inflation pushes it into sharper focus. Some proposals look for indirect signatures, like bubble collisions that could leave scars in the CMB. Others argue that statistical reasoning might favor certain inflationary landscapes. These ideas remain speculative, and the chapter must keep that boundary clear, because speculation is not the same as measurement. The best posture is curiosity with restraint, an openness to possibilities anchored by what the sky actually says. Even without bubbles, inflation already implies a vastness that reframes our earlier geometry discussion. Near flatness no longer looks like a coincidence, but like a consequence of enormous stretching. Our patch can look Euclidean because it was pulled taut, regardless of the larger universe's global shape, and that is both elegant and unsettling. It suggests that what we call the universe may be a local description, like weather on one continent. This returns us to the film's opening hook, now with higher stakes. At the top of the sky, where blue thins into black, the question is not only how far we can go. The question is whether far is meaningful when the universe can inflate beyond any map we can draw, leaving our best coordinates stranded inside one observable bubble. If the stage can expand faster than signals travel, then exploration becomes a matter of inference, not voyage. Inflation makes the edge feel less like a border and more like a limit of access. If inflation is right, then beyond the edge might simply be more universe, and far more than intuition allows. Our entire observable cosmos could be a drop in an endless storm of expansion and reheating, where new regions continually emerge with their own local beginnings. The camera can pull back until the familiar becomes a speck, then keep pulling back until even the idea of scale starts to wobble. That is the chapter's tension peak, and it is meant to be unsettling but disciplined. Inflation solves puzzles by making the universe larger than we can see and older than our earliest light. It also suggests that our cosmic address may be provincial, defined by one local ending of a process that continues elsewhere, beyond any signal we can receive. The edge, once a line on a map, becomes a property of causality. Yet the story cannot end on scale alone, because scale is still inside space and time. The hardest question waits behind the word outside, and inflation does not automatically answer it. If there is more universe beyond our horizon, it is still universe, still described by geometry and causality, and still subject to the same demand for coherent explanation. The deeper mystery is whether the concept of outside is meaningful, or whether it is a linguistic habit that physics will have to unteach. So we pivot toward the next boundary, one that is not merely distant, even if inflation suggests endless continuation. We must ask what it would mean for anything to be outside the universe at all. The next chapter confronts whether physics can describe an exterior, or whether the idea breaks the rules that make description possible. We carry forward the conclusion theme, now sharpened by inflation's implications. The universe may not end with a wall, and its edge may be written in horizons and geometry. Beyond what we can see is likely more cosmos, but beyond what we can define may be the true edge of knowing. At the very top of the sky, where the last blue thins into ink black, the question sharpens again. Does the universe have an edge? And if so, what could possibly lie beyond it? We keep reaching for the word outside, as if the universe were a room with walls and a corridor beyond. The metaphor feels natural because our bodies live inside containers, and our lives are measured by thresholds we can cross. But in general relativity, space and time are not the room's contents, like furniture in a hall. Space-time is the room itself, the geometry that defines distance, duration, and what counts as a straight path. That framing sets a trap that sounds profound and may be incoherent if taken literally. Asking what is outside the universe can be like asking what is north of the North Pole. The question assumes a direction that only exists inside the map, and the map is what we are trying to leave. Even the word where quietly assumes a spatial backdrop, which is exactly what relativity refuses to grant for free. Yet the urge persists because boundaries feel real in everyday life, and our senses are trained on edges. We cross borders, we leave atmospheres, we exit orbits, and we watch horizons cut off sight with clean circular lines. Even our language is built from edges, inside and outside, here and there, before and after. So the grammar itself pulls us toward walls. Earlier chapters turn edges into horizons of evidence and causality, not walls of matter, and that distinction matters here. Now we test the hardest version of the question. If space and time are part of the universe, then outside might require a larger framework than space-time, not merely a farther region. If no larger framework exists, outside may be a category error, not a hidden place. The unsettling possibility is that the question is not unanswered, but malformed, like demanding a color that is more red than red. The first boundary people imagine is the Big Bang, because it sits at the beginning of our cosmic story, like a dramatic opening frame. Popular language calls it an explosion, as if matter erupted into empty space and flew outward into darkness. That picture is vivid, and it is also misleading in a precise way that cosmologists have to correct again and again. Standard cosmology says something stranger and more constrained by mathematics. The Big Bang is not a point in pre-existing space with debris flying outward from a center. It is an early hot dense state where distances everywhere were smaller and where the same physical laws played out under extreme conditions. In that era, the universe was not in space the way a fireball is in air. Space was part of what was evolving. When cosmologists say expansion, they mean the scale factor grows as a function of cosmic time. Galaxies are not necessarily racing through space like shrapnel from a blast, propelled into a surrounding void. Instead, the metric that measures distance changes, so that the distance between co-moving points increases even if those points remain at rest in that coordinate sense. In plain language, the ruler stretches, and the stretching is built into the geometry. Visually, the difference matters, because our instincts are trained by explosions and projectiles. An explosion has a center, a direction of outward motion, and an empty background it expands into. The cosmological expansion in the simplest FLRW picture has none of those features, and it is homogeneous and isotropic on large scales. If you could hover anywhere in such a universe, the recession pattern would look the same in every direction. No arrow pointing to an origin. That is why center and edge do not apply in the simplest model, even though the word expanding tempts us to imagine a boundary. Every co-moving observer sees other galaxies recede, and the pattern looks statistically the same from any typical location. The universe expands like a rule for measuring separation, not like matter moving away from a privileged origin. The geometry changes and the contents respond, but the outside never appears in the equations. The evidence for this picture is not philosophical, and it is not merely aesthetic. It is written in redshifts in the Hubble-Lemaitre relation and in the near uniform glow of the cosmic microwave background. When we map the sky in microwaves, we see a temperature field that is almost the same everywhere, with tiny variations that later seed galaxies. Those variations are only tens of microkelvin, small enough to imply remarkable early smoothness, yet large enough to grow into cosmic structure. Those tiny variations matter because they show the universe had structure, but not too much and not too early. they also show it was once hot enough for matter and radiation to be tightly coupled like a foggy plasma that scattered light in every direction. Photons could not travel freely because free electrons acted like a dense curtain, constantly bouncing the light. When the universe cooled and atoms formed, the fog lifted and the CMB streamed freely. An image of a young cosmos stretched across time. The surface of last scattering is not a wall in space, but a moment in history when the universe became transparent. If we run the equations backward, density and temperature rise, and the early universe becomes increasingly extreme. The math points toward a beginning where curvature and energy blow up, and where classical descriptions lose their grip. That is the singularity of classical general relativity, and it is a warning sign rather than a photographed event. It is the theory telling us, in its own symbols, that we have asked it to speak beyond its competence. Singularities are not confirmed objects we can point to with a telescope, like a star or a galaxy. They are signals that the theory has been pushed past its domain of validity, where quantum effects cannot be ignored. When curvature becomes infinite, the equations stop being trustworthy guides, and the symbols begin to describe their own failure. In practice, physicists treat a singularity the way an engineer treats a broken gauge, useful for locating trouble, useless for describing what happens inside it. Historically, that lesson was hard won, and it reshaped 20th century physics. Einstein's equations allowed singularities, and early on, some physicists hoped they were artifacts of symmetry or mistakes of idealized models. Then the singularity theorems of Penrose and Hawking showed that, under broad conditions, gravitational collapse and cosmological expansion generically produce geodesic incompleteness. The mathematics said the edge was not easily avoided within classical gravity, even when you remove special assumptions. In other words, the problem was not a quirky corner case. It was built into the structure of the theory. This is where the film's logic must stay disciplined, even when the visuals tempt us toward myth. We do not have a complete quantum theory of gravity, and we should not pretend we do. We have candidate frameworks, partial results, and strong hints that quantum effects matter near the beginning. We also have a hard constraint. Any new theory must reproduce general relativity where it works, because it works astonishingly well. Near the Planck scale, the characteristic energy is so high that quantum fluctuations of geometry should be unavoidable. In plain language, space-time itself should jitter because the gravitational field is not separate from the stage. The classical picture of a smooth manifold may be an approximation, like treating water as continuous while ignoring molecules. What looks like a clean fabric at human scales may be a restless quantum foam at unimaginable resolution. So, the Big Bang may be a boundary in time, or it may be a limit of our description, like a coastline that dissolves when you zoom in. The question becomes whether time itself begins, or whether the beginning is replaced by a different kind of boundary condition. Either way, the edge is not a location you could fly toward with rockets, because it is not a place in space. It is a statement about what the equations allow, and about where the concept of earlier remains meaningful. Quantum cosmology tries to speak precisely where classical time breaks, without pretending the mystery is solved. It treats the universe as a quantum system with a wave function over possible geometries and field configurations. The goal is not to add fantasy, but to remove infinities and to state initial conditions in a language that remains meaningful. Instead of a single classical history, you compute amplitudes for many possibilities and then ask which histories dominate. One famous idea is the Hartley-Hawking no-boundary proposal, which replaces a sharp beginning with a smooth mathematical closure. Near the earliest moment, time behaves like a spatial direction in a Euclidean geometry, so the distinction between before and beside blurs. The universe has no initial edge in time, only a smooth cap, like the rounded top of a sphere where no point is a boundary. You can travel across the surface without ever encountering a literal edge, even though the surface is finite. In that picture, asking what happened before can be like asking what is south of the South Pole. The coordinate called time stops acting like time near the origin. So before is not defined. The beginning becomes a boundary condition, not a first event with a ticking clock. The unsettling twist is that the universe can be finite in a certain sense, yet unbounded, closed without being walled in. To visualize it, imagine a timeline that gradually loses its arrow as you approach the start. The familiar separation between space-like and time-like directions blurs, and the geometry becomes more like a four-dimensional surface without a sharp corner. The proposal is technical, but the intuition is simple. Replace a jagged start with a smooth closure. On screen, a sharp spike softens into a rounded dome, and the sense of first frame becomes a gentle curve. Other proposals use quantum tunneling language, borrowing a concept familiar from radioactive decay and barrier penetration. The universe can be described as tunneling from a classically forbidden state into an expanding spacetime, as if a barrier in the equations is crossed by quantum probability. The emphasis is on replacing a hard singular start with a calculable probability amplitude, even if the underlying interpretation remains debated. The math is not a storybook, but it does offer a way to trade impossibility for a tiny, non-zero chance. In tunneling pictures, the nothing is not an empty box waiting to be filled with stars. It is a limit in which classical space-time is absent, and the quantum description assigns amplitudes to possible emergent geometries. That is a subtle claim, and it is easy to misunderstand if we import everyday images. The word nothing here is a technical shorthand, not a philosophical declaration. These ideas are not experimentally confirmed, and they may never be directly testable in a clean way, but they aim at concrete problems, like why the universe is so smooth on large scales, and why it began in a low entropy state. They also suggest that the deepest edge may be mathematical, not spatial, and that the right question is about consistency rather than location. If the beginning is a condition, what selects it, and why does it permit complexity later? If time can change character, then outside becomes slippery, and our metaphors start to wobble. Outside usually means a place beyond a boundary in space, like stepping beyond a fence. But if the boundary is in time, outside becomes a metaphor for a regime where our usual categories fail, and where even earlier may be undefined. The mind reaches for a door, yet the door may be drawn on the wall. Still, physics keeps offering structured ways to extend the map, and not all of them require rewriting time. One route is extra dimensions and brain world models, motivated by string theory and by the demand for consistent high-energy physics. Here, outside can mean outside our familiar three-dimensional space, not outside existence. The point is not that reality ends at our horizon, but that our senses may be tuned to only part of the full geometry. In brain world pictures, our observable universe is a three-dimensional brain embedded in a higher dimensional bulk. Ordinary matter and light are confined to the brain, while gravity can propagate in the bulk. The outside is not empty. It is higher dimensional geometry with its own curvature and dynamics. If you imagine our cosmos as a luminous membrane, the bulk is the dim volume around it, shaping the membrane's motion. That confinement is not an arbitrary rule invented to rescue a metaphor. In many models, standard model fields arise from open strings whose endpoints are tied to the brain, while gravitons correspond to closed strings that can roam. The details vary, but the core idea remains. Different forces may live in different dimensions. In plain language, some interactions are trapped on the surface, while gravity can take shortcuts through the surrounding space. This changes what an edge could mean, because boundaries become about localization rather than termination. A boundary might be a limit of where fields are localized, not where reality ends. The universe could be finite in the bulk direction, or effectively infinite, while still looking three-dimensional to us at accessible energies. Even the word dimension becomes less like a direction you can point to, and more like a degree of freedom in the underlying description. The visuals here almost draw themselves, and the camera can linger on the contrast. We see a luminous sheet floating in a darker volume, with galaxies like sparks embedded in the sheet, then faint ripples, gravity, leak off the surface and spread into the surrounding space, returning as a subtle tug. The sheet flexes and the bulk responds, like a drumhead coupled to the air around it. But brain world ideas are constrained, not free imagination, and the constraints are surprisingly strict. If gravity leaks into extra dimensions, Newton's inverse square law can change at short distances because the field lines spread differently. Laboratory tests using torsion balances, measurements of planetary motion, and the behavior of binary pulsars all limit how large and how accessible extra dimensions can be. Even tiny deviations would have shown up as anomalies in precision experiments, and so far they have not. Cosmology also constrains them through the early universe, where small changes can have amplified consequences. Extra energy loss into the bulk can alter nucleosynthesis, the CMB, and structure growth, shifting the abundance of light elements or the pattern of acoustic peaks. A model must reproduce the observed expansion history and perturbation spectra, or it is ruled out by data that is already remarkably precise. The sky itself becomes a laboratory, and it is unforgiving. Even the absence of evidence becomes informative, because it narrows the space of possible outsides. When we do not see deviations in the CMB acoustic peaks or in the growth rate of galaxies, we learn that any extra-dimensional effects must be subtle. The outside, if it exists in this sense, is not allowed to be loud. It must hide in regimes we have not yet reached, or in effects that mimic known physics almost perfectly. Another route is cyclic and ekpyrotic cosmology, which reframes the beginning as a transition. Instead of a single origin, the universe undergoes repeated phases, or branes collide and rebound in a higher dimensional setting. The Big Bang becomes a passage, not a birth, and the edge becomes a turning point. The narrative changes from once upon a time to again and again, and that shift carries testable consequences. In some cyclic scenarios, expansion is followed by contraction, then a bounce that avoids a singular crunch. In ekpyrotic versions, a slow contracting phase smooths and flattens the universe before a bounce triggers hot expansion. The mechanism competes with inflation by offering a different way to set initial conditions without requiring a rapid early exponential growth. The goal is similar: explain smoothness and flatness, but the route is reversed in time. The ekpyrotic idea carries a specific intuition rooted in how energy components scale. During slow contraction, with a stiff equation of state, anisotropies and curvature can be diluted relative to the dominant energy component. In plain language, the universe can be ironed out before it reheats, so the high expanding phase starts unusually uniform. It is a counterintuitive claim. Contraction sounds chaotic, yet the equations can, in certain regimes, make contraction a smoothing process. But these models live or die by predictions, not by mood or metaphor, and the predictions are increasingly precise. They can imprint distinctive primordial spectra, including different tensor amplitudes and specific non-Gaussian patterns in the distribution of fluctuations. Evidence would come from precise measurements of the CMB polarization, large-scale structure, and any primordial gravitational wave background. The sky becomes a record, and we are learning to read its fine print. So far, the evidence does not force a cyclic conclusion, and the frontier remains contested. Inflation remains consistent with current data, and cyclic models face challenges in building stable bounces and matching observed perturbations. Uncertainty is not failure. It is the honest state of the frontier, where multiple ideas survive because the data has not yet delivered a decisive verdict. The deeper question is what kind of observation could ever distinguish a true beginning from a disguised transition. As the possibilities multiply, the central question tightens and the language becomes sharper. If there is an edge, is it a place you could reach or a boundary in the rules themselves? The most reliable boundaries we know in physics are not walls, but horizons. They are edges drawn by causality, not by bricks. Black holes teach that a horizon is not a surface you crash into like a cliff face. It is a causal boundary, defined by which signals can escape and which cannot. Locally, nothing special must happen at the horizon, yet globally, it divides the future into regions that can still communicate and regions that cannot. The eerie part is that the horizon can be invisible to someone falling through it, even though it is absolute for someone watching from far away. That is a hard concept, and it is also beautifully concrete when you see it in geometry. A horizon is drawn not by matter, but by light cones, by the geometry of possible paths. When space-time tilts those cones inward, outward becomes a direction that no longer exists for anything moving at or below light speed. The boundary is not a fence, it is the disappearance of an option. That analogy matters because our universe also appears to have horizons, and they shape what outside can mean operationally. In an accelerating universe, there is a cosmic event horizon that limits what we can ever influence. It is not the edge of space, it is the edge of causal reach, and it depends on the expansion history. The horizon is drawn by the future, not by a present-day wall. Horizon physics also carries thermodynamics, and that connection is one of the strangest bridges in modern theory. Black holes have temperature and entropy tied to horizon area and quantum fields near the boundary. Hawking radiation in the Beaconstein-Hawking entropy formula link gravity to statistical mechanics, suggesting that geometry counts information in a way ordinary intuition misses. A perfectly dark object becomes a thermal system, and the boundary becomes a ledger. A universe dominated by a cosmological constant resembles de Sitter space, which also has a temperature and an entropy associated with its horizon. An observer in de Sitter space perceives a bath of thermal radiation, not because space is filled with heat, but because horizons reshape what quantum fields look like. The vacuum is not empty in the naive sense. It is structured by the geometry of what can be observed. This is not poetic garnish. It is a quantitative claim with numbers attached. A de Sitter horizon implies a finite entropy bound for the observable patch, and therefore a finite number of effective degrees of freedom. It suggests that information and degrees of freedom may be limited by geometry, not by matter, and that how much can happen may be constrained by area rather than volume. The edge becomes a limit on accounting, and physics takes that accounting seriously. If the universe has horizon thermodynamics, then the edge is written in bookkeeping, and the story becomes almost austere. The boundary is about what can be known, stored, and transmitted across time. Meaning becomes physical, because information is physical, and physics keeps track of it with ruthless consistency. A thought-provoking question follows naturally. If information is bounded, what does that imply about the ultimate complexity of any future civilization? Here, the story returns to dark energy, introduced earlier as a driver of accelerated expansion and a mystery with precise fingerprints. We still do not know what dark energy is, but we can track what it does with supernova surveys, baryon acoustic oscillations in the CMB. It changes the fate of horizons, and it changes what outside can ever mean. The universe's long-term geometry becomes a prediction, not a guess, even if the underlying cause remains unknown. As expansion accelerates, more regions cross beyond our event horizon, and the separation becomes permanent. Distant galaxies do not merely get dim, they become causally unreachable. Their light can continue arriving for a time, stretched to longer wavelengths, but any signal we send now will never catch up to them. The outside is not a place we cannot see. It is a place we cannot touch, even in principle. Over cosmic time, bound structures like the local group remain, while other galaxy groups slip away like boats on a widening sea. The night sky would slowly empty, not because objects vanish, but because the expanding geometry stretches their light and cuts the causal threads. Stars still burn nearby, yet the grand architecture of the cosmos fades from view. The future astronomer may inherit a quieter universe and a harder puzzle. The edge of influence shrinks relative to co-moving distances, and that is a subtle but crucial distinction. The observable universe, in principle, can still grow in particle horizon terms, yet the set of things we can affect contracts. The future edge is not a rim, it is isolation, written into the equations of expansion. The universe can be vast and still become lonely, simply because of how space-time evolves. This is where the chapter's climax lands, and it lands with a kind of disciplined chill. If there is an edge, it may be made not of matter, but of causality. And beyond causality, physics becomes a different kind of language, one we are still learning to speak. The outside becomes less like a territory and more like a limit on explanation. That line is not surrender. It is a boundary marker that keeps the story honest. Causality is how space-time organizes explanation. By ordering events and limiting signals, if a proposed outside cannot connect by any causal channel, then its status shifts from physics toward metaphysics, because no observation could ever distinguish it. The scientific attitude is not to ban the thought, but to label it correctly. Yet the film cannot end on a refusal to ask, because the question is part of what makes us human. The disciplined move is to separate questions we can formalize from questions we can only phrase. Outside, the observable universe likely means more universe, governed by the same broad laws, unless evidence says otherwise. We should be wary of smuggling in drama, where the data offers only continuity. Outside space-time is a different claim, and it demands a deeper reworking of what we mean by where. It requires a theory where space-time is emergent, not fundamental, and where the word where is derived rather than assumed. Quantum gravity programs sometimes point that way, but none is complete, and each carries unresolved conceptual costs. The price of an outside may be a new definition of inside, so we inventory what each idea would imply if it were true, and we keep the ledger clear. No boundary and tunneling proposals replace a hard beginning with a smooth quantum condition, trading a singular event for a calculable boundary. Brains and extra dimensions turn outside into a higher dimensional embedding with testable leakage. Cyclic and ekpyrotic scenarios replace the beginning with recurrence and a bounce, with distinctive primordial signatures. Horizon thermodynamics ties edges to entropy and information, suggesting limits that look like geometry. Dark energy turns the future into a shrinking sphere of influence. Each proposal shifts the meaning of edge without giving us a simple door to walk through. The universe may be unbounded in space, yet bounded by horizons that define what can ever be observed. It may be bounded in time, yet not by a singular event, and it may be bounded in knowledge by the structure of causality itself. The most important edge may be the one between questions we can test and questions we can only imagine. We are left with a final, careful distinction, because clarity is the only honest ending here. There is the edge of space, which may not exist as a boundary at all. There is the edge of time, which may be a breakdown of classical description. And there is the edge of meaning, where our words stop matching the structure of the theories. Outside can be a useful prompt, but it can also smuggle in assumptions that physics rejects. The most mysterious answers often begin by correcting the question. Transition, after exploring possibilities, we return to what we can honestly answer, what lies beyond the edge, as defined by observation, and what remains forever uncertain. The next chapter will not offer a final map of the outside, because the outside may not be a place with coordinates. It will offer a final accounting of horizons, evidence, and the limits of inference. The resolution is not a wall at the end of space, but a clearer view of what it means to know. We return to the opening hook at the top of the sky, where black begins and familiar landmarks fall away. The question was never only distance, measured in light years and numbers on a screen. It was whether an edge is a place we could reach, or a limit built into perception. Tier 1 is the simplest answer, and it is also the most unsettling. No observation suggests a wall, a rim, or a seam where space stops and something else begins. In general relativity, space and time are not a stage that matter sits inside. They are part of the physical system, shaped by energy, pressure, and motion. Expansion does not require an outside container, because the metric itself can stretch. The classic balloon analogy is imperfect, yet it captures one key point. Every point can recede from every other without a center. Space can be finite without edges, like the surface of a sphere, or infinite without borders, depending on geometry and topology. That distinction matters, because finite does not automatically mean bounded by a wall. Tier 2 is the edge we actually have, and it is written in light travel time. The particle horizon marks the farthest signals that can reach us today, limited by the age of the universe and its expansion history. When we look outward, we look backward, and the view eventually runs out of paths to see. The cosmic microwave background marks a boundary in time, when the universe first became transparent and photons stopped scattering off free electrons. Before that moment, the cosmos was a hot plasma, opaque, bright, and crowded with collisions. The CMB is not a shell in space so much as a last scattering surface, a snapshot of a young universe about 380,000 years after the Big Bang. Beyond that surface, light cannot carry images to us. Only indirect messengers might. Neutrinos, gravitational waves, and the fossil patterns in matter distribution become the remaining ways to probe earlier chapters. Tier 3 is what we infer if the cosmological principle holds. The idea that, on the largest scales, the universe is statistically uniform. That principle was not always obvious, and it was earned through surveys that mapped galaxies into a web of filaments and voids. When we average over enough volume, the clumpiness smooths out, and the cosmos looks the same in every direction. Beyond our observable volume is likely more space-time, more matter, and more galaxies, arranged differently in detail, but drawn from the same cosmic rules. That is the level 1 beyond, mundane in content and unreachable in practice. It is not a cliff, and it is not a curtain hiding a different physics. It is a continuation past a horizon where the limitation is causal contact rather than geography. We reconcile the intuition that there must be a border because our lives are built from containers, coastlines, and doors we can cross. Human brains evolved to navigate rooms and landscapes, not curved manifolds and expanding metrics. Cosmology replaces that instinct with horizons, curvature, and initial conditions. concepts that feel abstract until you remember what they mean in plain language. The edge is not where space ends. The edge is where information runs out. Transition. After exploring outsides, we return to what can be stated with evidence. What would change the answer is not a new metaphor, but new data with clean statistical weight. Primordial gravitational waves would anchor inflation's energy scale and strengthen the case for an enormous beyond. Their imprint would appear as a specific swirl pattern in the CMB's polarization, a B-mode signal that is subtle and easily mimicked, a clean detection, separated from dust emission and gravitational lensing, would extend our evidence horizon earlier than the CMB's visible surface. Topology could also redraw the map, because global shape can leave repeating signatures. Matched circles or repeating patterns in the CMB would imply a compact universe with wraparound paths where light can traverse the cosmos more than once. The idea has a long lineage, from early geometric cosmologies to modern searches in satellite data. A measured deviation from flatness would point to a finite curvature radius and constrain the global shape, even if the universe remains unbounded. Each result would not reveal an edge, it would reveal the rules of the whole, rules that determine what outside can even mean. Some evidence would push us toward a stronger beyond, where inflation does more than smooth our patch. Bubble collision scars in the CMB would hint at eternal inflation and level 2 multiverse structure, leaving disk-like features or unusual temperature correlations, non-Gaussianity or unusual large-scale anomalies, could narrow inflation models, though cosmic variance limits certainty when we only have one sky to measure. These are frontier tests, not settled conclusions, and their power lies in how specifically they can fail. Dark energy is the other lever that can revise our story, because it controls the fate of horizons. If its equation of state differs from -1, the future horizon changes, and so does the long-term visibility of the cosmos. A time-varying dark energy could mean new fields, modified gravity, or a fate unlike de Sitter, including slower acceleration or more dramatic endings. Precision surveys turn that mystery into parameters we can constrain. By tracking supernova distances, baryon acoustic oscillations, and the growth rate of cosmic structure, Tier 4 is where language starts to fail, because outside may not be a coherent coordinate, and outside of space-time may be meaningless, like asking what is north of the North Pole. Grammatical, but not physically defined. No boundary ideas replace a first moment with a smooth quantum condition, where time behaves more like a spatial dimension near the beginning. Extra dimensions and brains turn outside into a higher dimensional embedding, constrained by gravity tests and cosmology, and by the stubborn fact that our everyday world looks four-dimensional. We keep these possibilities disciplined because mystery is not a license to say anything. Speculation is allowed, but it must stay tied to potential signatures and to models that make quantitative predictions. If a claim cannot connect to observation, even in principle, it shifts from physics toward metaphysics, and the narration has to mark that shift. The film's answer must label that boundary clearly, so wonder remains, but confusion does not. The future adds a final twist to the idea of an edge. Accelerating expansion creates a cosmic event horizon that limits what we can ever influence, even if we can still see some light for a while. Over time, distant galaxies redshift away, their photons stretched into wavelengths too long to detect, and they slip beyond causal contact. Future observers may inherit a smaller visible universe and fewer clues, surrounded by darkness that is not emptiness but inaccessibility. That makes today's measurements precious and historically unusual. We live at a time when the CMB is still detectable above foreground noise, when galaxies still trace the web across immense volumes, and when the expansion history can still be reconstructed. The edge of evidence is not fixed. It can erode with cosmic time as signals fade and the observable patch becomes more isolated. We return to the top of the sky, but the meaning has changed and the black looks different. The blackness is not a void beyond a wall. It is the boundary of what light has had time to tell us, written into the finite age of the universe and the speed of causality. Beyond it is likely more universe, and beyond that is a question about what counts as beyond. The central question resolves in layers, and each layer has its own kind of humility. There is no known physical edge like a barrier, at least none demanded by our best tested theories. There is a real observational edge written in horizons in the CMB, and it is as concrete as any measurement we make. Beyond the observable is probably more of the same if the universe is statistically uniform, even though we cannot verify that directly. And beyond what we can define, cosmology offers a different gift, one that is both rigorous and strangely personal. It does not promise a final map of everything outside our reach, because the reach itself is part of the physics. It teaches which questions are meaningful, which are testable, and which reflect the limits of our own language. Mystery remains, but it becomes sharper and therefore more human. We began where blue thins into black and learned that even space is not a doorway, but a gradient, a convenience line drawn across a fading atmosphere. From there, distance became time, and the cosmos revealed itself as a layered archive, parallax and supernovae, redshift and the cosmic web, all stitched together by the finite speed of light. At the farthest reach, the universe offered no cliff, only horizons, the CMB's last scattering veil, the particle horizon that expands with time, and an event horizon that dark energy may tighten, slowly erasing what can ever be known. We tested the shape of everything with the afterglow's geometry, finding near flatness that hints at inflation, and we followed that hint back to an early sprint of expansion that could have smoothed curvature, diluted relics, and frozen quantum noise into the seeds of galaxies. And when we finally asked what lies outside, relativity pushed back, reminding us that space and time are not a stage the universe sits upon, but part of the cast, with beyond sometimes meaning beyond meaningful language, not merely beyond a map. Yet the story did not end in surrender, because cosmology has a discipline even in its mysteries, turning speculation into signatures, matched circles, non-Gaussianity, bubble scars, and the faint possibility